Buongiorno, morning, bentrovati. Sentite?
Sì, la sentiamo.
Bene, adesso vediamo di mettere il tablet in condivisione. Dove è finita? Ah. Ok. Ok, adesso dovrebbe vedersi il tablet. Well, what do we have today? We have the last part of the attenuation properties of electromagnetic waves in plasma. And let's recap what we've seen last time. We always remember that we are expanding our solution on the basis of plane waves, which are described with a complex notation by an exponential. In this case, x is the direction of the wave, k is the wave number, so it's linked to the wavelength of the wave by the relation that k is equal to 2 pi over lambda. And then we have a term which is the oscillation in time that has the angular frequency of the wave, and here again we have the relation that 2 pi times nu equals omega. So here that we can go from the frequency of the wave in hertz to the angular frequency of the wave. In describing the electromagnetic waves, we found out that the dispersion relation written as a function of k, so k squared, had an imaginary term corresponding to the fact that we introduce a friction term in the electron Newton's law, accounting for the fact that electrons, due to collision with ions, are exchanging energy and momentum with the ion species. So somehow they are oscillating in the field of the electromagnetic wave and acquiring energy in half of the period of the wave, and then give it back to the wave in the second half of the period, if they are not colliding or losing energy. And the way they are actually exchanging energy with plasma is by means of collision. So by introducing this term, the relation that links k, actually the square of the wave number, and omega becomes a complex notation, a complex equation, and we divided the k number into two terms, one which is pure real term and the other one which is the imaginary part. So by splitting k in two terms, we reorganize the term of the exponential of the plane wave, and we find again an oscillating term describing actually the propagation of a plane wave in the direction of x with a wave number kr, which is actually 1 over, let's say, the 2 pi divided lambda, where lambda is the wavelength of the actual wave propagating. Omega is the corresponding angular frequency of the wave that satisfy the propagation relation. And then we had a term which is, in this case, if Ki is positive, then this represents a exponential decaying function as a function of the propagation coordinate x. So if we remember that the electric field is expressed as an amplitude times the plane wave, and if we remember that the intensity of an electromagnetic wave is proportional to the square of the electric field, then we see that the intensity of the wave is decaying with an exponential factor, and we call this factor alpha the attenuation coefficient. So we see that given, for instance, I naught, the intensity at a given point in the plasma, okay, this obviously could be any reference point inside the plasma, then if we keep on propagating the wave in the x direction, then the intensity drops exponentially. And we can describe this in terms of two quantities. First of all, alpha, the attenuation coefficient, that by comparison we see that is equal to twice the imaginary part of the wave number, or in other terms, instead of attenuation coefficient, which has a dimension of 1 over length, we can describe it as an exponential decay of the propagation coordinate divided a characteristics absorption length. So we say that the wave is attenuated, and where does the intensity of the wave go? Okay, this intensity goes into bulk energy of the plasma. So actually, we call this absorption length, or attenuation length is just the same for our purposes. So we have identified alpha as 2Ki, and we discover that this is linked to the plasma frequency of the wave. Then this down here is related to the refractive index. As you might see, this can be expressed as 1 minus omega p over omega square, okay? And this is actually mu, it's linked to mu, to the refractive index that we did analyze during the last lecture. So we require actually that in order to get to this expression for alpha, we have to satisfy a requirement which was hidden in our derivation. And it was hidden because the collisional frequency that we used is actually valid if the electrons are Maxwellian, as the one we used. So we have to guarantee that we are still in a regime where the electrons have time to relax towards a Maxwellian distribution, whilst they are acquiring momentum and energy from the electromagnetic wave. And this is exactly the requirement. So the rate at which electrons are exchanging the momentum among themselves, which is the order of magnitude of the electron momentum, linear momentum, divided the characteristic time for electron-electron collision, which is just by multiplying times the collision frequency between electrons, has to be actually, in order to be, for the electron to be Maxwellian during this process, has to be much faster, this rate, with respect to the exchange of momentum that comes from the interaction of the electron species with the electromagnetic wave that makes electron oscillating up and down. So this is the characteristic order of magnitude of momentum acquired by an electron during the passage of the electromagnetic wave times the collision frequency, and this is going to be the rate at which this momentum is lost by electrons to the ion species. Okay, we just played a bit with the relative scaling law of the frequencies and of the characteristic velocities. So for instance, the characteristic velocity for the electrons, which is the one that enters, if you remember, the collision frequency, we had that we have to estimate the relative velocity of the two colliding particles. These are electrons, so they are same mass particles, and the characteristic velocity is the thermal velocity. Okay, so it's thermal motion, and more or less is of the order of the square root of kBt divided the mass of the electron. On the other side, when we introduce the interaction of a free electron at rest in space hit by an electromagnetic wave, we find out that actually we found an oscillating solution. The electron is oscillating up and down in the direction of the electric field with a velocity which is oscillating with in time at the frequency of the wave, and whose maximum amplitude can be described as directly proportional to the electric field and inversely proportional to the inertia of the electron, so the mass of the electron and the frequency of the wave. Okay. Good. Then, in order to rearrange this equation into something that can be expressed in terms of macroscopic parameters that we control, and usually what we do is we prepare a pulse of electromagnetic waves. This is called basically, very in easy terms, a laser pulse, high intensity pulse of electromagnetic radiation. So what we can control more than the amplitude of the electric field inside the laser pulse, in optics, we deal with the intensity of the wave. Okay, so we want to express the electric field as a function of the intensities. So basically it's just the square root of the intensity of the wave. And we convert, instead of working with angular frequency, usually we work with lasers, for instance, not with the frequency, but with corresponding wavelength in vacuum. So we rescale everything. And what happened is that we found that this parameter here, the irradiance, okay, this is called irradiance, has to be smaller in order for the electrons to be Maxwellian than some factors, which is this constant term in front is a factor that contains all the physical constants. They are not changing, like the mass of the electron, the dielectric constant of vacuum, and the Boltzmann constant. So it's just a factor in front. But the scaling law is telling us that the irradiance is has to be smaller than the function that increases with temperature and decreases as the square of the ionization stage, maximum ionization stage, Z of the plasma. To be practical, we take as a reference the typical wavelength for lasers that we are using in ICF, inertial confinement fusion. And for optical radiation, we are talking about 1 micron radiation. So we see that the intensity that we have to require, so this term here, has to be smaller than 10 to the 14 watt per square centimeter. Okay, this term is the intensity. So we say that if we are in this regime where the intensity times lambda squared is less than 10 to the 14 watt per centimeter square per micron squared, then we are in the collisional regime. For I lambda squared less than 10 to the 14 watt per square centimeter per micron square. This micron squared is the arising from the fact that here we express the wavelength of the laser in terms of microns. Okay, so we say that we are in the collisional regime. So our derivation of alpha and propagation of the electromagnetic wave holds, where our derivation for electromagnetic waves in plasma holds. So it's satisfied. Okay, so we can put a date up here. Today is the 10th of May, 21. Oops. And so this is our framework. We obtained the alpha coefficient, the attenuation coefficient, working directly with the equation, with the dispersion relation. But now we are going to show that it's possible to actually obtain the attenuation coefficient using a power balance. So another derivation which has more physical content in it, and is a topic that we usually ask during the oral examination. So pay attention to it, because instead of using all the maths that we have to use to derive from the dispersion relation, we can actually get to the same solution, exactly the same solution, by using a more easy to remember physical argument. So let's obtain what is called power balance calculation of alpha. So the idea is, what is the power balance? So we have some competing terms and some ways of inputting energy in the plasma and some way of absorbing it. The power balance is a situation where we imagine to have reached the steady state, so that the net energy flux is conserved along the different steps. And the first steps, the initiating steps, is the electromagnetic wave coming from vacuum, for instance, or the laser coming from outside the plasma is entering the plasma and starts making electron oscillate up and down. So first is the electromagnetic wave interaction with electrons. Then electrons will start oscillate and redistribute energy within themselves. So we have a thermalization. And finally, we have the final step where electrons, due to collision, will give energy to the bulk of the plasma. So we they raise the temperature of the plasma. So there are these three steps that we can imagine. So we have the electromagnetic wave, and being a wave is carrying both energy and momentum. Let's suppose this is the laser coming and interacting with. We've seen that the main players in the electromagnetic wave interaction with plasma are the electrons. So why is that? Because they have a much higher mobility. The Q charge over M mass, the Q over M ratio is much larger for electron with respect to ions. So they respond immediately with respect to ion times. That's why we consider ions to be at rest in our description of electromagnetic wave interaction with plasma. So what the electron will do, they start oscillating up and down. Oscillations at a characteristic speed, which is the quivering velocity. And then electrons oscillating up and down in the field eventually collide among themselves and among the ions. So they finally will transfer energy to the ions. So this is the bulk of the plasma, where we want to absorb and store energy. And the mechanism for this is the collision. So again, the Coulomb collision that we studied at the beginning of our lectures. So we have to establish a power balance. So the energy coming from the laser given to the electrons has to be at a certain rate, has to be the same rate at which electrons are then giving energy to the ions. So locally, what we could state that we define capital E, the electromagnetic energy density of the wave, divided the characteristic time for absorption of the wave, tau abs. This is a power, a power density. So we have a characteristic energy density divided a characteristic time for energy absorption. So this is the rate at which locally the electromagnetic field or wave is losing energy due to interaction with the plasma. And we want this to be, this is the power balance, the same, to be the same rate at which we have the oscillation energy density of the ion, so the quivering energy density, divided the characteristic time for energy exchange, time of the energy. Okay, so with these symbols, you see that here we have an incoming power lost by the electromagnetic wave, and this rate of energy is exactly the same final rate at which the energy is coupled to the plasma. So this is basically writing an energy conservation equation in terms of powers. So there's no loss of net power, of net energy. The energy that this is just simply stating that the energy of the wave goes into the energy in the plasma. So we can rewrite this. We have a characteristic times here. Let's write them in terms of characteristic frequencies. So we have the time of absorption could be actually the frequency of absorption. So we have new absorption times the electromagnetic energy density, En, equals the characteristic time for energy exchange. So we can now state and remember what it was. This is the new EI, so it's the collision frequency of electron to ions, because this is the rate at which the energy contained in the motion of quivering motion, oscillation motion of the electron is transferred by means of collision to the ions. So this is the frequency we are looking for the energy exchange between ions and electron species. Okay, so what is the density of electromagnetic energy? So if you should remember that for the electromagnetic field, so the energy density is what we call U of the electric field is 1/2 epsilon naught E squared. Okay, there's a term in for the electric field, another term for the energy density of the magnetic field. Given the fact that the magnetic field is equal to the electric field divided by C, then we can combine the two into a single energy density of the electromagnetic field. Okay, this is the energy density of the laser. So we give it a name to this kind of electromagnetic wave, and it's much easier and simpler to just call it the laser, which we are, for instance, shooting from outside the plasma, and we want to couple its energy to the plasma itself. And what is the energy density of the quivering motion? So is the characteristic kinetic energy of the electrons in the moving in the wave times the electron density. So let's use a different color. So this the quivering would be the density of the bulk of the plasma. So N0 is just Ne, number of electrons, times the typical kinetic energy. So would be 1/2 mass of the electron times the square of the quivering velocity. As you can see, this is a characteristic kinetic energy of the motion, and this is the density. So expressing an energy density connected to the fact that the electrons are oscillating in the field of the laser. Then we can plug what is the value of the quivering velocity, and we can obtain the following relation, which is 1/2 N0, and then we have the quivering velocity. We wrote it somewhere. Okay, it's here. So it's E times E electric field divided the mass divided omega of the laser. So this is just, let's remember. So we have ME times E squared charge electric field squared ME squared omega squared. We can simplify, take one mass out, and what's left is 1/2 N0 E squared divided 1 mass of the electron times omega squared, which is the angular frequency of the wave. Okay, now let's work a little bit with the frequencies and put everything together. So we remember that we can express the way the intensity is dropping along the laser propagation is the intensity goes as, so let's say it's proportional. Oops. Goes as I naught e to the minus alpha x, which alpha is the attenuation coefficient we want to obtain by at the end of this calculation. So this is just I naught e to the minus x divided lam L abs, which where L abs is the absorption length. Okay. And we can express then alpha as 1 over the absorption length. And what is the absorption length? Okay, this is a very heuristic way of defining it. It's a characteristic length. And as always in plasma, we want to express this number as a function of characteristic time, characteristic speed, characteristic energy, and so on. So what is lambda absorption? We can imagine this is the characteristic length over which the energy of the wave is absorbed. So we can define it as, we have here the absorption time, so the characteristic time for absorption of the wave. And in order to get the length, when we have the absorption time, we need a characteristic speed in order to see how long as the wave have traveled during the characteristic time of absorption. So this is just the group velocity. Okay, this is interesting because it's a very simple argument where we use the property of the waves. One which we don't know at the moment, we want to actually find because it's linked to the attenuation coefficient. And we say that what is the characteristic speed at which energy travels with the wave. Remember that is Vg or V group is the group velocity of the wave, not the phase velocity, the one that actually describes the transport of energy and momentum by a wave. Okay, so this can be written as we write the a characteristic absorption time as the reciprocal of the characteristic absorption frequency divided V group. And V group is we find it last lecture. Okay, was this one here. You see that the group velocity for electromagnetic wave in plasma, so for the laser when it's traveling in the plasma as well, is C times the refractive index. So we can use this derivation and write our absorption frequency here, abs, divided C nu. Okay, now as you can see, we are deriving alpha at different steps. Now we have the given the laser, we know C obviously is a constant, mu as a plasma properties in here. Now we need the collision, the absorption frequency, but we can obtain the absorption frequency from the power balance we have written here. So you see that we can solve for absorption and then frequency. Then we say that the absorption frequency is the power density for energy exchange between electrons and ions divided the energy of the electromagnetic field. So let's write it. So this is 1 over C mu, and the absorption frequency will be mu EI times the power density, the energy density of the quivering motion, divided the energy density of the electromagnetic wave, EM. And then we can expand what we obtained before. So we have 1 over C mu. So this is the 1 divided the group velocity. Then we have mu EI, which is the collision frequency. Then we have the quivering motion energy density. So is, let's put it up here, 1/2 mu n0, the density of the plasma, characteristic density. Then we have electric charge squared, electric field squared times mass of the electron times omega squared. On top, at the denominator, we have the electromagnetic energy density, which is 1/2 epsilon naught times the electric field squared. Okay. Now, we can simplify what is the same factor. So 1/2 goes away. Electric field goes away as well. And then we have this, let's rewrite it, combining together these factors here, which are the plasma frequency. And so let's write it as 1 over C mu times the collision frequency mu EI times we have n0 E squared over mass of the electron epsilon naught, which is actually the plasma frequency, divided 1 over omega squared. Okay, so the term here is omega p squared, the electron plasma frequency, and we can write everything as, let's collect the okay, so we have collision frequency divided C, then we have omega P plasma frequency divided omega of the laser. Then what remains is mu, which is 1 over the square root of 1 minus omega P squared divided omega squared. Okay, and if let's go back and see what alpha was. We had it somewhere here, okay. See this formula here. So we have the angular frequency, we have the ratio of the collision frequency to omega, and then we have omega squared minus omega p squared. So this is actually, we can use one of these terms here and obtain mu EI divided omega. Then we have the omega p squared and 1 over omega squared minus omega p squared. So we used one of the omega here and brought it inside the square root. And this is actually exactly the derivation of alpha we had before. Okay. How do we got here? Basically, yes, okay, is by using a physical argument. So we stated that this power balance holds, and this power balance allows us to estimate the frequency at which the electromagnetic wave has to be absorbed, and we plug it inside the definition of alpha, and we finally obtain the same relation as before, the ratio of the electron of the collision frequency to the omega of the laser, so the angular frequency of the wave. Then we have the characteristic angular frequency of plasma oscillation, so the plasma frequency, and then a term that was the square root of this difference in frequencies, which is actually related to just the refractive index. Okay. What is the scaling law for alpha? So now we have this formula here, and we can rewrite alpha as, so we have mu EI divided C. Then we have a ratio of two frequencies, the plasma frequency squared divided omega squared of the laser. And then we have a 1 over the square root of the of this ratio here, which, if you remember, we can express omega squared as over omega squared as the ratio of critical to electron density to critical density. So we can rewrite it as 1 minus n of the electrons, density of electron divided the critical density for the laser, everything divided, everything to the minus 1/2. So this corresponds to 1 over the square root of that term. Okay. As you can see, this has the correct dimension. So we have this is a dimensional ratio. This again is a dimensional number. And then we have a frequency divided a speed. So this has the dimension of 1 over L. So it's 1 over the absorption length. So you see that if we highlight the fact that actually here we have a dependence on the angular frequency of the wave and of the wavelength of the wave. And here we have a dependence on the plasma electron density, which is here inside as well. So we want to discuss the scaling law for alpha. For alpha, where alpha is our attenuation coefficient. So let's remember that omega plasma goes as Ne as the electron density. Then let's remember that the collision frequency that we have in there is proportional to the electron density and to the temperature of the electron to the minus 3/2. See, now we are plugging in the scaling law in order to understand what is the scaling law for the alpha parameter. And then we have the relation that links omega to the wavelength of the laser. So omega is 2 pi let's use it. Frequency of the laser actually is, we use nu. Pay attention that this is not the collision frequency, but it is the frequency of the laser divided by, okay? And nu, we can express it as C over lambda, where lambda is the wavelength of the laser. So we see that omega goes, is proportional, inversely proportional to the wavelength of the laser, lambda. So we plug everything in here. So we have this dependence on the collision frequency. We have this one here on the plasma frequency. Then we can state that alpha goes as, let's say, a constant factor in front that, as always, is collecting all the physical constant like C, like epsilon naught, like the mass that is contained inside the plasma frequency. Okay, then we have that alpha goes as, we first write the relevant terms. So electron density times the temperature of the electrons times the wavelength of the laser, and then we have the final term as a function of the electron density and the critical density of the laser. And now we put the exponents taken from the scaling law of the different terms. So we have that, as you can see here, we have that you had that omega p squared goes as electron density, and then we have another linear dependence on the electron density coming from the collision frequency. So Ne goes as a second power. So alpha is proportional to the square of the electron density. Then is proportional, time to take a break after this small derivation. Then we have that there's a dependence on the temperature arising from the collision frequency. So it goes as the temperature to the -3/2. And here we have omega, and using this dependence here, we see that it goes as this wavelength to the second power. Okay, so now we have the scaling law for the attenuation coefficient alpha. After the break, we'll discuss when which are the most convenient way of having, for instance, the laser light interacting with the plasma, if our goal is that of absorbing most of the energy of the wave. So, we want to maximize the coupling of the incoming radiation with the plasma that is receiving that radiation and absorbing it. So let's take a 10 minutes break and see each other in 10 minutes time here again. Okay, here we are again. Can you hear me?
Yes.
Okay, so let's change sharing of the screen and the tablet again. Okay, during the break, I was looking at the formula we have written before, and okay, this is the for alpha. And what was puzzling me was the C at the denominator, which is correct here, as we check with a dimensional argument. But there's a C missing here. And so I went back to see where this was arising. So let's start, put the C back where they have to be. So put 1 over C here at the denominator. Can you see it? Yes or no?
Yes.
Oh, okay. So the problem was that a C was missing here. And let's go back a little bit. This formula here, there's a C missing as well, the speed of light. So let's put it here as well. That's why I was a little bit puzzled before, because I was using this formula, which had the speed of light that I was missing. And the origin of all of that we have to go back a little bit more, where we were working. Okay, here, this is the formula. So when I derived the formula here, we simplified at a certain time a C at the numerator with a C squared at the denominator, but I didn't bring it back, the C at the denominator. So we have to add it to this formula here. Let's put it here in front. Okay. So this was the origin of the missing C puzzle. And please correct the notes and remember to check that the dimensional argument, that the attenuation coefficient is the inverse of a length, then holds all throughout our derivation. So let's go where we were. I was discussing the scaling law of alpha, of the attenuation. So let's suppose we want to shine a laser, and our purpose is not of that one of just going through the plasma and have a diagnostic tool. So in that case, we have to use very hard radiation, like hard X-ray or gamma rays that just go straight through the plasma and do not lose that much energy. So it's a use of electromagnetic radiation for diagnostic purposes. But in inertial confinement fusion, for instance, we want to make the capsule imploding, and we want to couple as much energy as possible of the incoming laser to the plasma. So our goal in this case is to maximize the absorption. So the higher the absorption coefficient is, oops, I've lost the pen is not working anymore. Why is that? Let's check it. Okay, it's got lost connection, so I have to do this and force it back. Okay. Went down the charge. So let's give it just 10 seconds. In the meanwhile, let me continue saying what I was saying is that we want to maximize the attenuation coefficient. We are going to face two different situations. The first one is when we have a uniform plasma, and a uniform plasma is going to be a plasma which doesn't have any density gradient in it, so uniform density with uniform temperature as well. And we want to see in this case what is the best choice for the laser wavelength for obtaining a large absorption. And the other situation is where actually we are shining, for instance, a laser from outside a pellet, a fusion pellet, or we shine the laser on a solid surface, and the laser will turn the solid surface, that could be plastic, could be metal, into a plasma with a very sharp density gradient. In that case, we'll see that the choice of laser wavelength changes considerably. Okay, the pen is almost charged enough for another half an hour lecture. So let's see if we can get it back. Yes. Yeah. Okay. And silence the iPhone. And okay. Let's take this formula to the next page. And let's discuss the situation when we have a uniform plasma. Oops. So let's suppose to have a column of plasma like this, contained inside whatever. So we have a region of uniform plasma here. And we send through the plasma two different wavelengths. Okay, let's suppose that wavelength 1 is lambda 0, and lambda 1, which is going to be twice as lambda 0. Actually, what the half of lambda 0. So short wavelength and long one wavelength. So lambda 0 is going to be radiation of this kind. And lambda 1 has half of the wavelength, so it's going to be something like that. Okay. What is the attenuation? So, for instance, we send the light from right to left. Light is propagating, the laser pulse is propagating along this column and exiting the other side of the plasma. So, for instance, we want to see how much energy is being coupled to the plasma. So what we see here is that suppose we have a given density, okay, for our reference plasma, and let's suppose that the plasma is uniform. So Ne is constant. So it's not changing. And let's suppose the temperature is constant as well. So we want to focus our attention on the choice of the laser wavelength. So suppose we send 1 micron radiation here and half a micron radiation. Which is going to be absorbed most in the plasma? We see that these two terms are constant in this case. This is the plasma properties. Then inside here, there's a small dependence on the wavelength of the laser, but since it goes at the denominator under square root, we can neglect it for the time being. So the main terms, the main scaling law is with lambda squared. So we see that in this case, alpha goes as lambda squared. So increases with lambda. So if we increase the radiation wavelength, we increase the absorption. So in this case, for instance, the absorption of lambda 0 would be 4 times larger than the absorption of lambda 1. Okay. In our case, then the attenuation of alpha 0 is going to be almost 4 times the attenuation of alpha 1. Or let's say the attenuation of a short wavelength is going to be 4 times smaller than the attenuation of the longer wavelength. So for maximizing the attenuation, it's better choice to use longer wavelength. So if plasma is uniform, longer wavelengths are better absorbed. So for instance, instead of using optical radiation, like a usual transition neodymium glass laser, it would be preferable to use longer wavelength, like CO2 lasers that have a radiation in the far infrared, 10 microns radiation instead of 1 micron radiation, and we can get much higher absorption if the plasma is uniform. But so this is one choice. But actually for ICF condition, we face a completely different situation where we do not have a uniform plasma. And we want to couple energy to a very sharp density gradient plasma. So let's go to the second, let's describe first situation here. So case 1, and let's go to a case 2, where is a plasma with very sharp density gradient. Typical of ICF, inertial confinement fusion. So in this case, what is the situation? For instance, we have a pellet. We shine laser from outside in all directions. Like that. And starting from solid density, we have let's see if we can do it. We have a very dense plasma that rarefies progressively so that the density is dropping in the radial direction. Okay, like that. And obviously, yes, in the middle, we have very dense plasma here. Okay, so with the color gradient representing the density of the plasma, we see that the laser is coming from outside turning the pellet into a plasma, and we'll see in one of the next lecture that we have the plasma expanding towards the outside, so that if we take a line out in the radial direction and if we plot the density, we get something like this. So we have the density of the plasma as a function of the radial density, and the plasma density goes as an exponential. Okay, so we have here the density of the electrons. And we should, from outside, let's use the same color scheme as before, two wavelengths, lambda 0 and lambda 1. We have lambda 0 coming from the outside, and lambda 1 which has a wavelength which is just half of the wavelength of lambda 0. So let's recall what is the property of the plasma, of the electromagnetic wave propagation in plasma. We know that outside of the plasma, so basically in the outer layers, we are generating the laser in high vacuum. So we have that we have just optical propagation through vacuum, and there's no critical density. But then, as the laser is entering the outer layers of the corona and the density is ramping up exponentially, what is happening that we have to satisfy the propagation relation, telling us that we have a cutoff frequency, we have a cutoff in density, up to which we can propagate the laser. So let's remember what is the critical density. We remember that the density of the plasma has to be less than a critical density, which is equal to ME epsilon naught omega squared over E squared. And we can express as before omega as a function of lambda. So we turn out that it turns out that we can express it as mass of the electron epsilon naught 4 pi squared C squared divided E squared. So there's a lot of physical constant in this number. And then what it remains, what is the relevant part for us, is the dependence on the wavelength of the laser. And if you remember this, this critical density, we wrote it as 1.21 10 to the what was it, 21 electrons per cubic centimeter divided lambda squared in microns. Okay, an easy number to remember for those of us who are working with plasma physics. Remember that 1 micron radiation, so the typical laser wavelength, has a critical density of 10 to the 21 electrons per cubic centimeter. Okay, so the important thing is that besides these factors here that go into this final number here, then the dependence is with the square root of lambda. So you see that if we decrease the wavelength, if we go to half of the wavelength, then the critical density increases by a factor of 4. So the critical density goes 4 times the original critical density. So for instance, let's suppose that we are sending lambda 0, and this is the critical density of lambda 0. So let's draw this line here, corresponding to the N0 critical density, N0 critical. Then the critical density for lambda 1 is 4 times as large. So actually it would be 1, 2, 3, 4, okay. So more or less is up here. And this is the critical density N1 for wavelength lambda 1. So we can write it here that the critical density N0 critical is 1 over 4 N1 critical. So you see that if we send a laser with lambda 0 from the outside, it will stop where the density of the electrons is equal to the critical density. This means that the frequency of oscillation of plasma oscillation is the same as the incoming angular frequency of the wave. So what happens that lambda 0 cannot propagate beyond this region here, has to stop here, and most of it can be refracted or reflected. If you hit normally, then laser light is refracting and comes back. If you hit with an angle, it will just be refracted away and cannot reach actually the critical density. If instead we send lambda 1, which has half of the wavelength, we see that this radiation can propagate much deeper in the plasma up to its own critical density, which is 4 times as large as the critical density. So what happens is that although the absorption coefficient increases with lambda, so it's higher for lambda 0 than for lambda 1, the region that the two different radiation can access is different. It's not uniform anymore. And the important part is that the shorter wavelength can penetrate much deeper inside the plasma. So when comparing the two wavelengths, we see that actually there's a lot of path in in the difference of the two trajectory or to the two regions that the wavelength can access inside the plasma. So lambda 0 is stopped much farther out in the corona, let's say for instance here, whereas lambda 1 can reach much deeper inside the plasma. So in order to understand this, which is telling us that actually it seems that shorter wavelength can have a much higher absorption, let's re-express alpha, the attenuation coefficient, as a function not of the density of the electrons, but of the ratio of electron density to critical density. So then we can actually see a scaling law in terms of not just the value of the electron density, but of the ratio of electron density to the critical density. So what we can do is rewrite lambda as another constant factors, but we use the critical density. So what we do, we have lambda squared here, and lambda square is inside the critical density as well, okay, here. So we rewrite the coefficient in terms of a ratio of NE over N critical to the square times the temperature dependence, which doesn't change. This is just telling us something that relates to the actual plasma condition that we have prepared. And it's the same for different wavelengths. Then we have that lambda, the wavelength of radiation, as the same dependence, but as you can see here, we have 1 over lambda squared at the square root. So the lambda squared that we had at the top now goes at the denominator. And we have still the terms that is describing the refractive properties. So we have, and the cutoff as well, and critical to the -1/2. Okay, let's pay our attention to this term here, which actually is describing the fact that we cannot propagate at a density larger than the critical density of the electron. You see it because we have it as 1 over the square root of this term. So this has to be positive. So it means that the electron density has to be smaller than the critical density for that radiation. Here again, we have the cutoff properties are contained inside this term. Cutoff at NE equals N critical. So you see that if we compare the alpha coefficient written in terms of the accessible ratio of electron density to the critical density, we see that now the dependence of alpha it goes as 1 over lambda squared. So when we go to shorter wavelengths, they actually the absorption coefficient gets higher. So it's advantageous to use shorter wavelengths when the plasma has a very sharp density gradient, because shorter wavelengths can penetrate much deeper inside the plasma, whereas longer wavelengths have to stop much farther out in the corona. So they have less chance to interact with the important part of the plasma that are ramping up in density. So let's summarize this observation. We say that if we have, if the plasma actually, let's put the number 1 here. Let's repeat. If the plasma is underdense or uniform, what does it mean underdense? It means that the electron density is much smaller than the critical density. So we are far away from the cutoff, and both radiation will go through all the plasma anyway. In that case, if the plasma is uniform or underdense, then the cutoff doesn't come into play. And we've seen that longer wavelengths are better absorption. Long wavelengths are leading to higher absorption. The second case, especially for ICF, so if we have sharp density gradients, or when the plasma becomes overdense, so when the critical density is becoming of the order of the critical density, so the better choice is to go for shorter wavelengths. Are better absorbed. So in one case and the other one. So depending on the plasma condition, we have two choices, or going to short wavelength or longer wavelengths. In which direction we want to go? If we want to maximize the absorption of the laser of the electromagnetic radiation, that depends on what we want to do. If our goal is to maximize energy coupling of the laser to the plasma, then we have different choices depending on what is actually the plasma that we have to interact with. Okay, I guess this is it. And this concludes the topic on electromagnetic waves in plasma, where we discuss the propagation properties, the refraction index, the cutoff, and on one side, and on the other side, we've seen today what are the properties of absorption inside the plasma. Eventually, we link these absorption properties to the fact that electrons are oscillating the field of the laser light and losing energy, redistributing the energy that they are taking from the laser light, laser pulse into plasma temperature, plasma pressure, so plasma energy, by means of collision with the ions. Okay, let's change over to last topic on waves. We change completely of framework, and we move to a wave that is that involves the magnetic field only, and the speed and the bulk of the electrons only. So we have actually the fluid velocity in this case. So this is another kind of waves. They are called Alfvén waves. And the novelty with respect to what we've done up to now is that these waves are very large in amplitude. So we are not going to use the usual technique of obtaining the laser propagation. Oh, I'm seeing that actually the size of the screen is somehow small. You didn't comment on that. Let me try to start again. I don't know for what reason the player just was acquiring half of the portion of the screen. Okay, now seems to be better. And let me share again the screen with this one here. Okay, looks larger. And okay, let's give it a title. So this is going to be Alfvén waves. So I was telling you these Alfvén waves are mixing the fluid velocity in where we are going to use MHD equation and the magnetic field only. So is another interesting case where at the beginning we studied electrostatic waves, if you remember, where we had only electrons and electric field playing together, and the magnetic field was not taking part in the wave phenomenon, and these were longitudinal waves. Then we studied transverse waves, where we have actually electric and magnetic fields. So we have electromagnetic fields interacting with the plasma, so light waves and optical radiation and so on. And now, in order to conclude this overview of the possibilities to produce, to generate waves in plasma, then we are talking about waves where we don't have the electric field, we have only the magnetic field interacting with the plasma. And if you remember the lecture with Atzeni, this is exactly the framework of MHD, magnetohydrodynamic, where we have that the electric field actually is hidden inside the equation by assuring local quasi-neutrality. The electric field disappears, and we face a system in MHD where we have a magnetized fluid. So the plasma is represented by a fluid, single fluid with a given density, a given bulk velocity. The charge is constantly balanced, so we don't have charge imbalance inside the plasma. And this fluid is interacting with the magnetic field. So we have that we are going to use ideal MHD. So what does it mean? If you remember, ideal MHD means that the resistivity goes to 0. So we don't have energy losses in due to resistivity. The magnetic field is not diffusing, if you remember, since the resistivity is connected to the capability of the magnetic field diffusing across its own field lines. So ideal MHD you can imagine as a situation where we have the plasma fluid, we have the externally applied magnetic field that somehow constrains the evolution, the propagation of the fluid. And if you remember, in the evolution of B, there was a term that we called as frozen in flow. So actually, in idea MHD, the almost time to take a break, and then we start again. In idea MHD was saying that the fluid elements are rigidly advected together with the magnetic fluid. So they are really linked together, and there's a strong interplay. So we say that, and we comment on this at the end of this lecture. We say that actually the B field lines are very rigid lines. The B field, magnetic field, behaves like a field of forces, and the field lines are represented like strings. So like strings of a guitar, for instance, with a very high tension. And when you pluck a guitar, then you have that the perturbation goes along the string, and you have the propagation of a wave inside along the string, and the propagation is transferred to the string. This is going to be exactly what we are going to see in Arfan waves, where the string are represented by the B field lines, and the propagation of the wave will be a modulation of the magnetic field. It will propagate along the string, so along the externally applied magnetic field lines. So let's take a break, see again in 10 minutes, and then we start obtaining the wave solution for our Arfan waves. Are there any questions? Okay, let's take a break and see in 10 minutes time again. Okay. Welcome back for the last slot of today. Can you see the tablet and hear me?
Yes.
Oh, okay, thanks. Okay, so we were introducing Alfvén waves. So we say we are going to work in the framework of ideal MHD, and this means that the resistivity is going to be zero. Then we are going to assume the presence of an equilibrium B field, so an externally applied magnetic field. So at equilibrium, we will have a magnetic field, we call it B0, or the externally applied magnetic field, which for our purpose here is going to be just directly along the Z direction. So it's going to be a B0, the amplitude, along the Z direction. So, oh, no. Okay. So we have the Z direction, and actually we'll put the Z direction in a direction of the externally applied magnetic field. So we have a, like this, P0. Is going to be a vector in the direction of Z, and this is B0. And we will look for solution of waves where the propagation vector k is proportional to, is parallel, let's say, to the direction of B. So this is going to be the direction of the wave solution. B in this reference system, B note, is going to be 0, 0, and B0, represented by this vector here. And it's going to be a constant vector. So this is the equilibrium solution that is not changing in time and space. We look for what? Longitudinal waves. Sorry, for transverse waves. So our propagation direction will be along the B note lines, B0 lines, and we look for transverse plane waves. What does that mean? It means that propagation direction will be along the z-axis, and the quantities that will take part into the wave phenomenon will be oscillating in direction perpendicular to the B field lines. So this means that the components of the wave are not a function of the transverse direction, so they are constant in planes which are normal to the propagation direction. This can be represented by telling by saying that the differential operators, the partial differential operators along x is 0, and the partial differential operator along y is 0. So actually our nabla operator in this condition will be 0, 0, and dz. So we allow for a change in value of the wave only along the propagation direction, which is z, but along in the transverse plane with respect to the wave, the wave will have a constant value. So this is equivalent to say that we are looking for transverse plane waves. Planes will mean that the wave, the value will be constant in planes transverse to the propagation direction. Okay. Another assumption is actually, this is important, we'll say here, we are not using the linear approximation. We do not use linear theory. And this is one of the important points which makes this derivation interesting, because up to now we always used to linearize around the equilibrium state, saying that, for instance, the velocity, the amplitude of the wave, of the electric field, of the magnetic wave, were much smaller than the equilibrium values. And this, in terms, meant that the amplitude of the wave has to be smaller with respect to the equilibrium values. Think, for instance, of the acoustic waves. The acoustic waves are small perturbation in pressure with respect to the atmospheric value of the pressure, so the atmospheric pressure. If you increase the amplitude of those acoustic waves, at a certain stage we reach a situation where our derivation is not working anymore. We are not going to describe this in our course in plasma physics, but just to tell you, if you increase the amplitude of the sound waves, at a certain point you reach the limit when you have what is called the shock wave. So the perturbation is moving at a speed which is higher than the speed of sound. In this case, the theory is not linear anymore, and to describe shock waves, we have to actually use a different kind of approach. But this that we are going to introduce today is a derivation where we do not use the linear theory. In the end, this will lead us to saying that actually the amplitude of the Feld waves can be very, very large. They can transport quite a lot of, we see, for instance, magnetic field with them. So they will have a very high significant impact on the plasma dynamics. They are not going to be just local perturbation, but they will really manipulate the structure of the magnetic field. That's why they can be very, very important to control and to understand them, especially in magnetic confinement fusion. So we don't use the linear theory, but what we do, what we require, for instance, is, this is another of our assumption, is that the fluid is incompressible. So we use incompressible fluid. And this means that, what does it mean that the fluid is incompressible? It means that the fluid lines, the velocity line of the fluid, are not converging or not diverging. They are not focusing to a point, which means compressing the fluid elements, nor diverging, it means rarefacting. So we can express, for instance, if we have fluid elements going this way, we will see a rarefaction of the density of the fluid. And in other case, if we have fluid lines pointing to a given point, then it means that the fluid in this motion here is compressing. So we have to assume actually that in our case, the fluid elements are propagating along straight lines, more or less. So they are not nor rarefacting nor compressing the fluid. And this corresponds to the fact, that's why we depict these lines as this, that in incompressible fluid, there's no divergence of the velocity field. So incompressible fluid, this one here, means that the divergence of the velocity field of the fluid is zero. Okay. So another way of stating it is if you go and look for the continuity equation, the total derivative along the element fluid is zero. So the density of the fluid is constant along the fluid lines. If we then assume that the fluid is incompressible, it means we can translate this into a property of the differential operator as well. So let's see, we said that the divergence of the velocity field equals to the scalar product of the nabla operator that we have just defined as a subset of the differential operator for plane waves, is just the derivative along the z direction dot the velocity field vx dy dz. Let me see if I put the timer. Yes. Okay. So we don't overshoot. And by taking this scalar product, you see that the incompressibility of the fluid leads to the requirement that the z velocity component, the z component of the velocity is not changing in z, so it's constant along z, so it's equal to zero. So Vz is constant. So we're going to neglect it because a constant term is not of interest for us. It's like a uniform drift. It's not representing a wave solution that is traveling inside the plasma. So for us, means that Vz is going to be zero. So Vz being constant, it could be just the constant drift velocity along the B field line. So what are the, at this stage you understood what are the partners that are making up this phenomenon of wave, Alfvén waves. On one side, the magnetic field, and now we are discussing the velocity field. So Alfvén waves will see the interplay of B field and the fluid velocity, V. Okay, so for us, the fluid velocity will be will have a zero speed along Z. Okay, and let's now describe what is the total electric magnetic field. Sorry, so B total. So the one that enters the MHD equation will be the superposition of two fields. One, which is the externally applied B field, and the other one is going to be the magnetic field that is representing the Alfvén wave. So this will be a function of Z only, as we said, since we are looking for transverse waves, and of time. So we have that B naught is going to be the externally applied field. and B is going to be the wave solution. Let's say this is the equilibrium value of the B field, and this is the superposition of the equilibrium value plus the wave. But we do not write, as we used to do in the past, the previous derivation, the the wave solution is small with respect to B0. We just leave it like that. So there's no need for it. And let's write it in components. Then we have that the external applied magnetic field in our frame of reference, which is directed along B0, has just the Z component corresponding to the external applied field and is constant, plus a solution that for us is going to be Bx, By. So it's going to be transverse solution. So it won't have a Z component. It will have just two components in the transverse direction with respect to the original B field. So we can, using the color code, say we have Bx and By, the component of the wave, and then we have the constant value of the external applied field. This is the total magnetic field seen by the fluid, and this is the magnetic field B that enters actually the MHD equations. If you remember, one of the fundamental equation for the magnetic field is that we're now requiring that magnetic field doesn't have monopoles. So it means that the divergence of the magnetic field is zero. This is a fundamental equation for B, saying that B is a solenoidal field. Let's see what this corresponds to. We say that the total B field has to be solenoidal, B dot. And it means that since the Nabla operator, as we've seen, is just the derivative, partial derivative along Z, it means that the Z over BZ is equal to 0. So BZ is constant. Okay. And exactly what it is, B0. It's the externally applied field. And the wave solution won't have any contribution along the Z direction. Okay. So we need some dynamical equation now to couple the magnetic field to the plasma fluid. So one of them is the Faraday's law, which we can write it as a function of, in terms of a derivative of P. So we can write it at the time derivative of the magnetic field. And we use B dot to remind us that this is the total magnetic field, equilibrium state plus wave, is equal to minus the divergence of the curl of E. Okay, this is the Faraday's law, written in terms of the time derivative of P. And if you remember, now we have to make this electric field disappear in MHD equation. So we use the Ohm's law. So in Ohm's, Ohm's law is, let's write it in a okay, is for ideal MHD is in general is equal to E plus V cross B dot equal eta j. But since we are in ideal MHD, this corresponds to requiring that E plus B cross B equals to 0. So the electric field is linked to the curl of V cross B dot. Okay, and we can plug this expression for the electric field directly into Faraday's law. So let's go down here, and this becomes minus the curl of, and substitute minus V cross B dot. So we made the electric field disappear, and we obtained an equation that links the magnetic field and the velocity field of the fluid. So this is plus V, the curl of V cross B dot. Obviously, we put a bracket to stress the priority of the vector product, which is important here because it's not the curl of V cross B dot, but the other way around. Okay, so we have that our time derivative of B is equal to the curl of V scalar product to B0 plus V vector product B of the wave. Okay, by using this notation, we put B dot as the total B field, and in the following, when we see B alone without any index, this is going to be the wave that we are going to look for. And so the wave solution, and V is going to be the field velocity field. Okay, so we have to compute this cross product here. So let's do the cross product of V cross B dot. So we want to compute V cross B dot, and the derivation of affine waves is full of this vector product. So we're going to start with the first one. So we have the usual technique using the determinant. So ijk, we put Vx, Vy, and 0, the component of the first vector. Then B dot, which has a component Bx of the wave, By of the wave, and B0, the external applied field. And we take the denominator, the determinants. So we have that actually, let me put this on the side here. So first term is this determinant. So it's B0 times By times B0. So the X component is going to be Vy B0. Then the second one is the determinant of this one here, Vx B naught. minus 0, but we have to change the sign. So this is becoming minus dx b naught. And the z component is the determinant of this minor here. So it's going to be vx by minus vy dx. Okay, this is the vector representing the first product. Okay, now we have to take the curl of this vector. So we do it again. And let's use a different color. So we have to compute the curl of V cross B dot. So this time our denominator will have ijk. Let's call it, okay, the first operator is going to be 0, 0, dz. This is the component of the first vector. And the second one, let's call them, use this color scheme to simplify. Let's call this vector ax, ay, az. So this is going to be ax, ay, az. And we're going to have this vector here. So first component, let's take this determinant here, which is 0 minus dz ay. So let's write it here, dz ay as a placeholder. Then the second one is 0 minus, it was a minus as well here. Let me check. Yes, is minus dzay. Second term is second component there, so the y component is 0 minus dzax, but I have to change the sign. So plus dzax. And the last one, no, sorry, it's this one here. See, we have 2 0 here, so it's 0 and 0. So the z components is easy, and it's just 0. Now let me translate what is ay, and this component here. So we can write, first component is minus times minus makes plus, dz dx b0. So I use this and plug it here. Now I have dz times ax. Ax is by times b0. So n is plus, again, plus dz by b0. And the last one is 0. Okay, now let's have a look. And you see that since b0 is constant, can come up, and we see that we can write this term as b naught, the externally applied field, times the z derivative of what? Of the velocity field, which has these components here. Okay, this is the wave representing the wave component of the fluid velocity. And we see that actually we can plug everything together and see what was this terms was the Faraday equation. So our Faraday equation, this one here, can be written as the total derivative of B dot equals to this term here. Let's focus our attention to the total derivative with respect to time. Sorry, not the total, the derivative with respect to time of B dot. I swap total with the derivative. So this is the derivative with respect to time of Bx, By, and B naught. Since B naught is for hypothesis a constant, this term is 0, and we see that the derivative of time of B dot is just, since B0 is constant, is equal to the derivative of the wave part of the magnetic field. So let's combine together this term, which is the left-hand side term, and the right-hand side there. So let's put them together, and we say that finally we derive the fact that we obtain that the derivative with respect to time of P, of the magnetic field wave, is equal to B0, the amplitude of the external applied field, times the derivative with respect to Z of the velocity field of the wave. This is one of the wave that we of the equation that we want to obtain, and we call it equation 1. As you can see now, we are moving in the right direction. If you remember, what is a wave phenomenon? That the time derivative of a quantity is influenced by the space derivative of the other one. So this telling us that the time derivative of B is linked to how the velocity field is changing in space along the B field lines, along Z. And now we're going to derive exactly another equation like this, mixing the terms and exchanging V with B. So we'll find another equation that links the time derivative of P, of V, this time of the velocity, with the spatial derivative of P. And then we can set up the wave phenomenon where an anisotropy in V produces a change in time of, so a source term for B, which in turns can be will lead to a space derivative for B that will in turn be a source term, so for the velocity field, and this will set up the wave phenomenon, just the same as what we've seen in factorize, let's say, the wave operator in 1D when we had the progressive and regressive wave. Here we have the first half of the wave equation. Now we have to get the second half, and we have to use another dynamical equation. For B, we use the Faraday's law. Then now we need a dynamical equation for the velocity field. So we are going to use the fluid momentum equation, which is the dynamical equation for the velocity field. So we use the fluid momentum equation. Exactly, it's the same procedure that we use for the other wave derivation. We need some dynamical equation that are linking together the quantities that are giving rise to the wave. So in this case, the fluid momentum equation is telling us that the acceleration of the fluid, which is rho, the mass density of the fluid, times the time derivative of the fluid velocity v. There's only this term. You know, you might have seen that in the MHD that you were requiring the total time derivative, but we had just figured out that the advection term is 0 because the fluid is incompressible. So there's only this term surviving the total derivative. So it's just the explicit time derivative of the velocity fluid is equal to what? To the forces acting on the fluid. So the first forces that we have is the gradient of the pressure field. So we have a pressure gradient, and obviously the force acting on the fluid is in the direction opposite to the density pressure gradient. So this is P, and the other one is rho, plus the J cross P force acting on the current carried by the fluid, J cross B. And now let's remember that this is B tot, okay? In the dynamical equation, we have to put both the external applied field and the field of the wave. Because not assuming that the B field of the wave is a small perturbation, we have to include that in the dynamics as well. Okay. Let's recall what is the magnetic force. So this term here. So J cross B which is called the magnetic force, is equal to, okay, we can plug directly using Ampere's law J. So J is equal to the curl of B divided mu naught cross B dot. See, what we used here is the Ampere's law. And you might have asked yourself, okay, that's Ampere's law, but where's the Maxwell Ampere's law? So where's the displacement current that's gone? Okay, the displacement current is linked to the electric field, to the time derivative of the electric field. And that is a term that arises only for very fast phenomenon, when we have that actually the phenomenon under consideration is evolving on a time scale which is comparable to what? To typically the oscillation of the electromagnetic field. So we reintroduced that terms into the derivation of the electromagnetic field, because actually we were describing a phenomenon which was very, very fast with respect to the dynamical properties of the plasma. In this case, we are using MHD equation, so fluid almost to take times to take a break, almost to the end of this slot as well. So we are focusing on interaction of the B field with the fluid, and we'll find out actually that the speed of Alfvén waves is small compared to the speed of light. So that it makes sense at this stage to say that we are neglecting the Maxwell term in the Maxwell and Ampere's law, and we're using only this term here. Okay, so what is this term? We can obtain what? B dot is, let's write it again, is represented by Bx, By, B0, the external field, and we have to compute the curl of p dot. So curl of b dot is equal to, let's put it, I, j, k, 0, 0, dx, and then we have bx, by, b0. And this will have the following components. For the x component of the curl of b, we see that this is 0 minus dz by minus dz by. This is the first component. Second component along y is the determinant of this one here, 0 minus dz bx. We have to change the sign, so plus dz bx. And then we have the last term, which is 0. Okay. And we stop it here. Now we have the left vector, which is this one here, the right vector, which is p naught, and we have to take the curl, so another vector product using the components. So let's stop it here, and we reconvene next Friday for finishing of this Alfvén law, and then we'll talk briefly about the rocket equation. Are there any questions? If not, then we see again next Friday. Take good care. Have a nice day.
Arrivederci.
Arrivederci.
Arrivederci.